Today I'll be going over an implementation of a Siamese neural network with VGG16 model. And although I'm not a machine learning engineer, nor is this a machine learning channel, I recently had an opportunity to work on this project to cluster different screenshots based on their semantic similarities as shown in this slide. So I grouped different screenshots based on their semantic similarities and also classified outliers, which was not part of any of these campaigns. But the implementation here that I'll share is only a part of the entire project. So I would say it's not perfect, but it's definitely a good starting point for whoever is trying to implement a Siamese neural network in Keras. So let me actually start with a very quick conceptual idea behind Siamese neural network. So we have a triplet of anchor, positive, and negative image, which we would then pass through each of the neural networks. And then we would compute the distance through a distance layer and then pass that into a triplet loss function, which would then try to minimize the distance between the anchor and positive pair while trying to maximize the distance between anchor and negative pair. So once the model is trained, we can make predictions by passing in different inputs into each of the network, and we would get output for each of the network. Then we can use cosine similarity to compare each of these outputs. So if the input images are the same, we would have a similarity score that's closer to 1. And if the images are different, we're going to have a similarity score that's much lower compared to the similarity score here. So that's the whole idea behind how the model is trained and we can make predictions with it. So let's actually get started with how it's implemented. So the first part here is really just all the import that you need. And the second part is the initialization of the GPUs if you're using them. And then this part, we have the preprocessing class, where we actually read the data and form all the triplets. So inside this preprocessing, we would pass the path to the data source as its parameter. So under this directory, I have a bunch of different directories where each directory contain the same group of screenshots. So I had used about 23 different clusters or 23 different directories, and I used total of about 8,600 images resized to this specific image. So if I were to just look at this in order, what happens is it receives a data source, saves it into the data source variable, and then it calls the self.preprocessing function. So what preprocessing function does is read the dataset. So this read dataset is right here. So when we read the dataset, we would list the directories that from the data source that we pass in as a parameter. And then this part is really just to optimize a little bit. We actually predefine the arrays so that we don't continuously append to the existing array. So I just define these arrays and then just loop through the directories and then loop through each of the images in the directories. And then I'll load the image and then convert it to an array and do a resize using the OpenCV library. And this preprocess input function is actually from the VGG16 preprocess input. And this is necessary if you're using VGG16. And then so we would have the X array that contains the preprocessed image, as well as a Y array that's the label or the directory. So that's what the read dataset function would return. And then from back in the preprocessing function, we would actually call the list on the set of the labels. And then I'm just doing a sort. If your directory names are not integers, then you don't need this. But then this can be helpful if your directory names are integers like mine here. Or actually they're string values, but then I'm just sorting them out. And then I would create a dictionary where we have a label and then as such. So what this label dictionary is doing, if I have or you have a directory that is not in order, so it's not like it's not incrementing one at a time. So if you have a directory like this, what this would do is actually just map each of the numbers to 0, 1, 2, 3, 4, 5, and so on. So that this would map to 0, this would map to 1 as such. And then from here, this would map to 7, this would map to 8, this would map to 9, 10, 11, 12, and so on. So that just helps kind of sort things out, make it clearer for you later on. And then defining the array of labels into a new array. And this part is just shuffling the data set. So once it actually returns, it will be stored in the training images variable and the training labels variable as such. We also have the unique train label, which is the every label, unique label that we have, as well as the map train label indices, which would map each of the label to the indices of the training images. So this will come in handy when we are trying to generate the triplets. So let's actually look at how the triplets are generated. So we have the get triplets batch function where we define the number of triplets we want. So you can set this number higher if you want, but if you have any computational limitation, then it's better to keep this number low. And later I'll show you how you can kind of iterate your training process multiple times, even if you have a smaller number of triplets. So what this does is in a loop, it will call the get triplets function. And then inside the get triplets function, it will choose two labels from the unique training labels, namely label L and R. So this would represent different directory or different cluster each. And then from label L, we select two images, or these are actually the indices of the training images. And then we choose one negative label, negative index from the other directory. So this ensures that this N is from a different directory from the anchor and the positive index. So this is anchor index, this positive index, this is the negative index from the training images. So this would return 3 different values, which would then append to different arrays. And then these arrays will be selected from the training images separately and then transformed into the TensorFlow dataset, which we then zip into one single zip dataset as such. So this will just give us a zipped dataset as such. So once we are done reading the directories and the images, we can call this get triplets batch function. So we're trying to visualize these triplets to make sure that triplets are generated as we expected. So we would get a zipped data set, and then we can actually get a single element from this data set. And this would give us an array of anchor positive and negative images. And this is an array because if you remember, this anchor data set is actually an array of data set, right? So this would be an array of anchor. And then I'm using the show function and the subplots function to really just plot them out and see if the triplets look as expected. So these are visualization of a triplet. So each row represents a triplet. And I know this looks a little bit distorted. That's probably because of the preprocess input function that I'm calling here for the image. That's why the RGB is flipped. But you can kind of infer that these two images are the same because this is the anchor image, this is the positive image, and this is the negative image. And we can see some kind of similarity here and so on. So moving on to the actual implementation of the model. So this part is a model that was defined in this blog post. So I'll put the link to this blog post in the description box, of course. And this is actually the blog post where I got this preprocessing code from. That's where I inferred all these code from. I did make some changes to it. But if anyone wants to refer to the original post, that's where I got it from. So there is a link to a Git repository. And then inside the Git repository, they are using the specific model that is just 5 layers of convolutional layers. So this is the implementation of that layer. But then the problem with this standard simple model is that it accepts a fixed shape of 224 by 224. So if you have images like mine, where it's a screenshot and it's quite complicated, resizing the image will actually distort the image, and this kind of model will not be very efficient in terms of recognizing the similarities and differences between images. So that's one of the problems I faced with the implementation at first. So I'm actually using transfer learning to call the existing state-of-the-art VGG16 model. So I'll just comment this out since we're not using it. But with the triplet loss class, we define the embedding, which is the model itself. And we're calling VGG16 include top false and trainable to false. And then this is the interesting part. So along with this part here, we have the input defined with a shape equals none. And we actually pass the output of the VGG16 as an input here to this convolutional layer with kernel size equals to 1. And this is actually the fully convolutional layer that I actually briefly mentioned. And there's a blog post regarding this implementation of fully convolutional network. So what it essentially does is to allow us to have an input of any size, basically. So if you read this blog post, it talks about how the model usually requires an input of size 224 by 224 or somewhere around 512 by 512, and they're all fixed. And what this network allows us to do is actually it does not contain any dense layers. Instead, it contains one by one convolutions that perform the task of fully connected layers. So with the absence of dense layers, it makes it possible to feed in variable inputs. So if we just pass in the parameter of any size we want, the accuracy of our training goes up. And that's one important implementation that's included here. That's why the size of the input is none, and so on. But I'll put a link to this blog post, of course, in the description box. And there's also a video that talks about how the one-by-one convolution works. So I'll put that in the description box for your reference. And there's also a fine-tuning function that you might want to use, but I actually had it here, but I didn't make use of this. But it's there for your reference. So this is the model. This is the model that we have. So now we have the distance layer class that computes the distance between the anchor and positive pair, as well as the anchor and negative pair. And we also have the Siamese model class that actually modifies the training step of your fit function. And everything I have here is actually from the official Keras documentation that talks about the triplet loss. So if you scroll down, it really gives you all the examples where you can actually define a distance layer, as well as the Siamese model class that they use to modify the training step and computing the loss and so on. So I'll leave this up to you to read on your own time. So that's all about the model and the Siamese loss function, triplet loss function. And then here we have the training process. So this is a little bit unique in our case because if you look at this, I have defined a train loop function that has a loop of size that I pass in, which is 50. So it loops through 50 times to call this fit function on the training dataset. And I only define an epoch of size 5. And the reason for doing this is because of the triplets that I am generating here, because I was limited to the number of triplets that I could define because of the computation power that I had with my machine. What I instead wanted to do was actually just call this multiple times in a loop so that I can call triplet batch multiple times and kind of increase the variability of combinations, if that makes sense. So what I'm really doing here is calling the model, and then I have a path to save the weights for the models. And I call this training validation dataset function that I define up here only once. And one important thing here is that this 500, this number here, has to match the number n here, because we have 500 triplets. And what's happening here is I'm actually taking the first 80% of those triplets and defining that as training dataset, and then skipping the 80%. So the last 20% is the validation dataset. So because I know that I have 500 triplets, this is not a good implementation, I know, but just keep in mind that this number has to match the number of triplets that you have defined up there. So this really just defines the training dataset and the validation dataset, and call the batch and prefetch function on those datasets. So once I define the training and validation dataset, I define the anchor positive and negative inputs as such. And then with inside this train loop function, of course, I'll skip the first iteration, but then from the second iteration, I'm calling this triplets batch function again, and then loading the weights from where I had saved earlier, and then compute the distances and specify that as the output in the model. Define the Siamese network, which you then pass into the Siamese model, and just run the fit function. And then you would define path and save the weights in the path that you provided. And I know this part doesn't make too much sense right now at a glance, but honestly, this part is quite confusing. A lot of this is brought in from the official Keras documentation. So please take your time to understand how this part is implemented. And you can, of course, take the training part out of this loop. This was just how it had to be done for this particular project. So if you look at this output, we actually start from quite a high loss as well as the validation loss. But through iterations, we actually get to the point where we have a loss close to zero. And of course, if we had more iterations, that could give us a better result. Once we are done with the training, I call the get triplets batch and get a single element to get an array of anchors, positive and negatives, which I pass into each of the embedding as such. So one thing to note here is that we are passing the image into embedding, although we actually trained the Siamese model architecture itself. We are making use of the embedding that's inside the Siamese model. So we call the expand dimensions on each of the images so that it fits into the embedding. And then what I'm really just trying to do is pass the anchor and positive embedding into the cosine similarity function to see if we get the score that we kind of expect. So we get 0.99 for the anchor and the positive embedding, and then a smaller score for the anchor and the negative embedding. So this looks okay. And what I did next was really just visualize each of the triplets along with the similarity score. So I would call the cosine similarity for each of the anchor and positive, anchor and negative pair, and call the show function to display the anchor positive and negative image. So this really helps you with visualizing where you're at with your triplets and the similarity scores. And as you can see, it's not perfect. Some results are pretty good, but if you look at a result like this loop 7 or loop 9, the similarity score of the positive pair is pretty much very close to the negative similarity, although this image is very different from the anchor image. So once we are done with the visualization, I generate a non-shuffled test data set for later use. So I'm really just reading the data set and just calling the preprocessing function. That is very similar to what we used to have in the preprocessing class above. And I just get a test images non-shuffled as well as the labels that's not shuffled. I also get a test labels and the mapping of the non-shuffled data set. And you'll see what I'm using this for later towards the end. But once we are done preparing that, I just read the actual test data set and the preprocessing function, which I call and pass in the path to the test data set that I had. So I'm only using about 7 test directories in this example. And again, I'll define the unique test labels and the mapping of the indices. And once we are done with that, I am defining a matrix that will help us with the clustering. So here I'm going to pause for a second and bring you to this page that talks about the DBSCAN. So DBSCAN, there's a library under sklearn. So DBSCAN is a density-based spatial clustering of applications with noise. And all you have to know is this is density-based spatial clustering. So I won't go into too much depth on this, but what's happening is that you will define a epsilon value as well as the minimum samples value. And then DBSCAN will make use of these parameters mostly to determine the points that are close to each other and form a cluster based on how dense they are together. So there is actually a blog post that talks about the DBSCAN and how you can use it, which I'll of course share in the description box below. But as you can see, DBSCAN accepts a distance matrix and perform the clustering. So this is a very good unsupervised clustering algorithm for this specific project where we have the distance matrix. So what we have inside the matrix is the similarity score, or actually the distance between each pair of the test images. So I define a nested for loop and call the cosine similarity. And then between the images with the R index and the C index from here, I pass it into the embedding and then compute the cosine similarity and then store it in the matrix at row and column as specified. And the reason I'm doing 1.0 as such is because I did see some values that go over 1.0 for some reason. So that's why I have this line here. And then this would only define the upper right triangle of the matrix. And I just want to copy the upper triangle of the matrix to the lower bottom triangle. And this really just helps us with saving the computation power that we're using. And then I'm normalizing against the minimum value. So I get the minimum value from the matrix and normalize with this. And then I'm actually subtracting this normalized similarity score from 1.0 because this is the distance between the images. And because the distance is the inverse of the similarity score, that's why I'm subtracting this from 1.0. So by then I have the matrix, which I'll actually show the visualization of later. But then once we're done with that, we have to find the optimal value for epsilon. And this epsilon, as I mentioned, is the parameter for the DBSCAN that goes in here. And we can actually use an algorithm to find the optimal value for epsilon. Although I don't think it is very helpful, to be honest, but at least it gives you an idea on which epsilon value that you might want to use. And I'll share this blog post that talks about finding the optimal value for epsilon as well. So once you kind of visualize this on a graph, then you would simply call the DBSCAN function and pass the distance matrix along with the epsilon value and the minimum sample values. And then what I try to do is kind of fine tune this epsilon value as well as the minimum sample values to get the number of clusters that match the actual number of clusters that I have. So here you can see I have 7 different clusters that is generated, or 7 different cluster labels that is generated from DBSCAN. So this I wanted to match with the number of the directories I had. So this is something you just have to fine tune, and it's better if you can keep the value as high as possible for both. But it really depends. So you have to kind of play around with that. And using this cluster labels that I have here, I would sort it and then sort the enumerated cluster array based on the first index, right? So what is happening here, just to help you visualize, is that I have a cluster labels that I got from the DBSCAN, and then when I enumerate through it, what I'll get is, for I in sorted enumerated cluster, let's just print I and see what this gives us. So it gives us the index on the first index, and then it gives us the actual cluster label as a second index. So I am sorting this this array based on the value on index 1, which is the second values here. So that's what I'm sorting by, and then I just want the index of, or the indices of, this sorted cluster. So that gives us the sorted cluster labels, which we then use to actually sort the test data set as well as the labels. And we would sort the distance matrix. We rearrange the rows and columns of the distance matrix using the sorted cluster labels. So that will kind of rearrange the rows and columns and form a cluster of images. So this is the matrix before sorting or clustering. So this is the old matrix that I had. And as you can see, you see black squares along this diagonal line. That's because these values along the diagonal line represent 0 distance, meaning that it's comparing an image to itself. So if you compare the image to itself, of course you have a distance equals to 0. That's why it's black squares along the diagonal line. And then when I try to visualize the distance matrix that has been sorted out, it forms a bigger square along this diagonal line. So that means that the images has actually been clustered together and form a cluster. So if you see something like this, that means the clustering has somewhat been done. And then I can go ahead and visualize these clusters. What I'm doing here is just getting the first index of each of the cluster and then visualizing each of the triplets. So each row would be one cluster. And as you can see, we see some clustering done, although it's not perfect. And once we're done with that, we can go ahead and visualize the triplets along with the similarity scores. And that's where I'm using the non-shuffled dataset as I defined above in the beginning. And then, pretty much just the same approach I used above. And I would just visualize these triplets along with the similarity score. But as you can see, it's not perfect for some of the triplets, although for others it's not too bad. So the model actually distinguishes images that are very different or very similar. But when it comes to images that are quite similar, like we kind of visually know that these images are semantically the same, but we get a low similarity score because these buttons are different and so on. So it is not perfect in that sense, but we at least have we're at least at a place where we can, improve on. So if you have ideas or suggestions on how you can improve this architecture, feel free to comment down below and try things out. So the last part is actually testing the accuracy by generating image pairs and then making a predicted labels, and then comparing the validation labels with the predicted labels using the Jagged score, and also using the recall, as well as some manual comparison. But as you can see, it's not perfect, as I mentioned, but we are at least a step closer to building this Siamese neural network. And that actually wraps up this video. If you have any questions, feel free to comment down below. Thank you all for watching.